Hey guys, welcome back to Calculus. So we are nearing the end of this stuff. Just a few lessons left. Today we are going to dip our toe in the water of differential equations. And next lesson will be similar to that, related to that. The very last one will be over basic polar coordinates, and I encourage you to investigate that more thoroughly on your own because those are kind of interesting. And they are useful when you are doing things over circular kind of geometries in the future. But today is just an introduction to differential equations. So, warm up today is reviewing Taylor series, of course. Find the Taylor series for the function x squared centered around 3. And then 2 and 3 are trying to solve for y. You're trying to get y by itself. Now, these are examples of differential equations. They're first order differential equations. By that, I mean they involve first derivatives, just one derivative of y. But it relates x's and with a function y and the derivatives of y all together into one kind of equation. And your job for solving a differential equation is to try to figure out what the function y is that satisfies such an equation right there. So let's go ahead and practice. Number one, we're just going to find a Taylor series for x squared centered at 3. Taylor series is all about the derivatives of your function at the number you care about, at 3 in our case. So 0th derivative is obviously didn't take a derivative. That's x squared. First derivative would be 2x. Second derivative would be 2, and so on and so forth. But they all go down to 0 after that. Evaluating these derivatives at 3, the 0th derivative at 3, the function at 3 is 9. First derivative at 3 turned out to be 6, and the second derivative at 3 turns out to be 2. From then on, the derivatives are all 0. So, how do you write this function? Well, let's see. This top one is a master equation for something that's a Maclaurin series. This is not a Maclaurin series because our centers are not 0. Our centers are 3. Nonetheless, it's the same idea. The function, which is x squared, is the 0th derivative, which is 9, divided by 0 factorial times x minus 3 to the 0 or 1, so just that term, plus the first derivative at the center, which is 6 over 1 factorial times x minus 3 to the first, plus the second derivative at my point, which is 2 over 2 factorial x minus 3 squared. And since the subsequent derivatives after that are all zeros, they don't matter. Cleaning things up a little bit without the factorial, that means that x squared can be rewritten around 3 as x minus 3 squared plus 6 times x minus 3 plus 9. So no matter what function you got, doesn't matter. You're just taking a bunch of derivatives over and over again, plugging in what it is at the center, and if it's a Maclaurin series like this model right here, that means it's centered around 0, so it's just x minus 0 to the first, x minus 0 squared, x minus 0 cubed. There's just x's basically. But more generally, if your center is not 0 down below, it's the same idea, only it's just x minus 3 and x minus 3 or x minus your center, whatever it happens to be. Okay, now for the new stuff. Let's attempt to solve this differential equation. Now, the only ones you're going to be asked to solve are very straightforward, simple, first-order, separable differential equations. What do I mean by separable? It is possible to get everything with y's on one side of the equation and everything with x's on the other side of the equation. That's why it's called separable. You're going to separate things. Put the x's on one side and the y stuff on the other side. Now, when you solve these, here's basically the key, and this is a pretty simple lesson today. You're going to let the differential guide you right here. In order to get y's on one side and x on the other side, this side has a y and an x, a dy over dx. To start moving things around to the other side, you would probably multiply through by the bottom dx. So once you multiply through by dx, ask yourself, are all the x stuff on one side and all the y stuff on the other side? Well, certainly on the left side, it's just y stuff. Over on the right side, you got a dx and you got an e to the x plus 2. It's all x stuff. So you got all x stuff on one side, all y stuff on the other side. Once you've done that, you've separated things out, and you can just slap an integral on these things to undo the differentials, and you'll see what you get. So obviously, the integral of dy is just y. The integral of e to the x plus 2 is e to the x plus 2x. And do not forget your arbitrary constant. They are going to be very important in this section. This is why the plus c has always been important to write, because when you actually solve something, there's an infinite number of answers to this. You could have an infinite number of solutions because you could have an infinite different number of c values. But sometimes they'll tell you something about the function. The function at 0 has to be this, or the function's derivative at 5 has to be this. They'll tell you something called a boundary condition. So you can plug things in and figure out what c is, and you've done those before too with like projectile motion problems, you start with acceleration, you go up a level, they tell you something about the starting velocity, you can plug it in, figure out what the constant is, and go back up the chain from there. It's no different here. So today is going to be actually pretty straightforward, and I think the lesson and the homework is going to be pretty easy. Okay, trying another one. Number 3, solving for things. Now you got x's and y's on both sides here. Okay, so, but again, let the differential kind of guide you. The only way to get rid of something that's differential here is to multiply by dx. So you multiply both sides by dx. It means the dx is over here. But does this side only have x's then? It's got a cosine x. It's going to have a dx, but it's got this divided by y. So over here, you got the y stuff, so you need to move this y to the other side. Multiplying through by y and dx. Then on this side, you'd have a y squared dy. Great, all y stuff. On this side, you would have a cosine x dx. Awesome, all x stuff. So you've separated your variables out like this, and you can finish it from there. Slap an integral sign on this thing. And the integral of y squared is 1/3 y cubed. Integral of cosine x is sine x. And then again, always make sure there's a plus c on one side or the other. You don't need 2 plus c's because a constant, you can just subtract it over and a constant minus a constant over a constant. But you have a plus c here. And you don't know what the c is, but that's okay. Can you still solve for y? Yeah, you can. Solving for y, multiplying both sides by 3, then you'd have a 3 sine x plus a 3c. Now 3 times a constant is just another constant. So technically, maybe I should call this c1, and then 3 times c1 is c2 or something like that, but I'm being a little sloppy with it. A constant times 3 is still a constant. But you don't y solve for it yet. Y cubed is all this stuff. So how do you undo the cube? With a cube root. So y is equal to the cubic root of this entire thing under here. Note the plus c is under there too now. 3 sine x plus c, all of that cube rooted. So as soon as you get done with your integral, you put a plus c on there. And then if you can, sometimes you can, sometimes you can't. If you can solve for y explicitly, and by that I mean just say y equals blank with x's, great, do that. Sometimes what you've got done is a mix of x and y's, and there's no good way to solve for y explicitly. So you could leave it like something like this and have an implicit solution like this. But we don't want an implicit solution if possible. If possible, go solve for y. If not possible algebraically, just leave it be. So that's what we're going to talk about today, solving differential equations like that. Very easy. You probably already get the gist from the warm-up. Learning goals, introduce the differential equations and their applications to science. Your homework over Taylor series 8.2 is due today. This stuff over differential equations, separable ones, is going to be due on Friday. So you got a few days on that one. Due on the 1st. We are winding down the calc class. Okay, so things that were outstanding need to be turned in. Any old homework that you fell behind on, get them in. Extra credit is going to be a cutoff by Wednesday the 6th. Okay, I want you guys all wrapped up by that end of that week. So 5/7, 5/8, something like that. I want everything turned in. The course should be over. This is a college course, so I'm going to get the grades in the Neosho and get that all finalized, and you guys are free because it's a senior level course too, so seniors are done early. So by the end of next week, the 8th at the very latest, I want all things wrapped up and turned in, so make sure that you are staying on task. And if you've been doing so, and everybody's getting caught up, and I appreciate that, I'm still behind on grading, I'm working on that. But you guys are doing a good job, keep it up. And those extra credits, if they're out there, EC.1, EC.2, those were both assigned a long time ago. They're posted way back in the thread on Google Classroom at the bottom and stuff like that. But these are extra credit opportunities. So if you've got a 0 on something, or something's outstanding, or something got you, or the test didn't go as well as you wanted, or you just want to bump your grade up a little bit, then you're welcome to work on either of them. They're worth 10 points a pop. So that's like 2 assignments with the extra credit. One is pretty straightforward and easy. One's kind of long. But if you're interested in extra credit, those will be cut off by Wednesday the 6th, so get those turned in at your convenience. Stuff from today, separable differential equations due on Friday the 1st. Okay, here we go. So here's a differential equation. It is an equation relating a function to its derivatives and some independent variable. So here, this is examples of differential equations, or gross looking things. Here you have this is a second order differential equation. The reason it's called a second order is because you have second derivatives involved in this thing. So whatever the highest degree is of the derivative involved, that's what order it is. Now you're not going to be expected to solve anything like this complicated. I don't think I could. I don't know many. This is just made up. I don't think anybody can solve this one, honestly. There's a lot of differential equations you cannot solve. But nonetheless, this is something like that. It relates some function y to how the function changes with respect to some other variable and that other independent variable itself. So it's just a mix of x's and y's. Be warned also, a lot of times in differential equations classes, they don't use y as a function of x, they use x as a function of t. So there might be a bunch of t's floating around and dx over t's, but it's the same concept. And the reason they quite often have the independent variable be t is because things depend on time, and usually differential equations are modeling things that change with time. This one down here is another example of it. This is, like I said, sometimes things depend with time. So in this case, x is the function, and it depends on t, so x is a function of time. And this might be an equation for a damped harmonic oscillation. If you're a physics kid, you might recognize this as mass times acceleration right here. This is like a sum of forces. This is a weight. This is a resistive kind of force for a spring or something like that. And this might be the motion of a spring set in motion with some kind of damping, or maybe just some harmonic oscillation, and it would go up and down like a sine graph would be a solution like this. But the point is that you can get some really complicated differential equations, but a lot of physical equations are set up as differential equations because you do know something about maybe not x, but maybe you know about something about its acceleration or something like that, which is the second derivative. And if you can set things up as a differential equation, find a solution to it, then that'll tell you the mathematical model that will actually physically represent what's going on with this kind of thing. Okay, so yeah, differential equations are very complex, and sometimes they don't have an explicit solution. It means you can't just say, okay, y equals f of x. You can't just do that. But one of the most basic ones, you can do that typically. And the only ones you're going to be expected to solve today are called by the method of separating the variables, which I already alluded to in the warm-up. When solving, get all of one type of variable on one side, all the other type of the variable on the other side. If you can get all the y's on one side and all the x's on the other side, great. Then you can integrate and put an arbitrary constant in. And if there's an initial condition, there is something they tell you about the function at a certain input, or what the derivative of the function is at a certain input. They'll give you some piece of information sometimes and sometimes not. So if they give you a piece of information, you might be able to plug it in and figure out what the arbitrary constant is and not write a plus, like +4 or some kind of number that specifically models that scenario. And we'll see some examples like that. And let's just dive in, okay? So it's no harder than that. We got 4 examples to look over today. The first 2 are just straight up differential equations. The second 2 are also differential equations, of course, but notice that these 2 initial conditions are given. They're telling you in number 3 that y, when you plug in 1 for x, you should get out 1 for y. And they're also telling you in this one, number 4, that when you plug in 0 for x, you should get out e for y. So they're giving you some initial conditions. These bottom 2 will not have constants in them because, well, they'll have constants, but we'll be able to figure out what they are because you have these initial conditions and we'll plug them in. The first 2 don't have any initial conditions. They don't tell you anything. So there's an infinite number of constants that could be chosen. So we'll leave it as a general solution with just some arbitrary plus c in those 2. All right, here we go. Number 1. So first things first, you need to separate the variables. You need to get all the x stuff on one side and all the y stuff on the other side. Now, what should guide you is this derivative itself right here. To start getting these y's and x's separated, the only way to do that would be to multiply by dx. That means that there'll always be a dy on the left, and so all the y stuff needs to go on the left. And since the dx moved to the right, all the x stuff has to be on the right. So if you have any other x's or y stuff, you need to move them to the appropriate side right here. So like we said, if you multiply by dx and there's a dx on this side, but there's still this y up here, so you divide both sides by y also. And notice we just did whatever we had to do algebraically. Treat these just like fractions, multiply where the bottoms, because they're set up that way, and the way we kind of have this terminology, or dy over dx, is set up so you can move things around and do things like that. But once you get all the y's on one side and all the x's on the other side, slap an integral on it, and you're going to undo the derivatives that way. Integral of y dx is 1/2 y squared. Integral of 1 over x is natural log of the absolute value of x plus a constant. Now try to solve for y if you can. If you couldn't, then you would just stop right here and have an implicit solution. This is an implicit solution. It's a mix of x's and y's. It doesn't just say y equals. But if you can, try to move things around and get y equals and get an explicit solution. So how do we do that? Well, we got this half for the y squared, so we'll multiply both sides by 2. Again, a constant times 2 is just another arbitrary constant. And since you have a square, you got to take a square root. Don't forget your plus or minus, of course. So there are two possible branches to this. There's a positive root that might be a solution to this. There's also a negative kind of root that might be a solution to this. So there's the actual inverse, or the actual solution to this isn't really a function. It fails the vertical line test. In fact, if you look up this is more of a relation right here, but that's okay. We can have a plus or minus, and which one would we choose? Well, depends on what the initial condition is they gave us. They didn't give us an initial condition, so I don't know which one. I can't plug in numbers, and I can't figure out which one makes sense, a plus or a minus, so I'm just going to leave it like that. That's the final solution to that. Number two, same idea. Here's a differential equation, dy over dx is sine x cosine y. So start by multiplying both sides by dx, so move the dx to this side. But then it's got a cosine of y in it, doesn't it? Well, I don't want that. This side should all have x's. So dividing by a cosine of x, which is same as secant, then dividing by the cosine of y gives you a secant y on this side. So you got secant y dy. On this side, you multiply by dx on both sides, so you have a sine x dx. Slap an integral on these things. Integral of secant y with respect to y is natural log of the absolute value of secant y plus tan y. Over on the other side, the integral of sine is negative cosine, so of x plus a constant. Now, oh gosh, how in the world am I going to try to solve for y in this case? I don't know if we can, but let's do the best we can. So I see that all this y stuff is buried inside this natural log. So let's undo a natural log by doing e to both sides. So e to the left is e to the right. Now watch this little trick right here. When you have something raised to a power and the power has something plus something, you can undo your exponent rules. You can write that as e to one of them times e to the other. Because what do you do with your exponents when they got the same base? You can add them together. Well, we can undo that adding. So if you have negative cosine of x plus c, I can write that as e to the c times e to the negative cosine of x. But what's e to a constant? It's just some number. It's another constant. So I'm going to call that c. So in general, I have e to the natural log of the absolute value of secant y plus tan y is a constant times e to the negative cosine. But of course, on the left, the e and the natural log cancel out. And I have the absolute value of secant y plus tan y is a constant times e to the negative cosine of x. When you have an absolute value of something equaling a number, that means the stuff inside the absolute value is either plus or minus the number. So I can drop the absolute value and put a plus or minus in front of this constant. But again, since it's a constant, who cares if I make it positive or negative of a constant? It's still some constant. So this is about as far as I can get. And if you have some algebraic way to solve secant y plus tan y equals something and isolate y, I'd love to hear it. But I think this is about as good as we're going to do as far as getting a explicit solution. It's not explicit. It doesn't say y equals, but this is as far as I can go in my work and actually, try to solve for y. This is the best solution I got right here. So secant y plus tan y is some constant times e to the negative cosine of x. That is a solution, a relation that would solve this particular thing. I don't want to say function because I don't know what it looks like. Graphing that would be really complicated. I'm sure it's some kind of relation that fails the vertical line test or something like that. But you see the process, and that's all that basically is to it. Now, last couple examples, it's the same idea. Okay, we got a differential equation here, and we're going to solve it, but they have boundary conditions. So this is something you can use to figure out what the arbitrary constant should be. So in this one, x squared dy over dx is y squared. Again, multiplying by dx to move it to the other side. Well, then the dx is on the right, and the dy is on the left. So when all the y stuff on the left, all the x stuff on the right. So this y squared is on the wrong side, so I got to divide by y squared, but this x squared is also on the wrong side, so I got to divide by x squared. So on this first equation, if you multiply by dx, and then divide by the y squared and divide by the x squared, then you have separated the variables successfully, and you have all y things on the left and all x things on the right. Slap some integrals on these things. The integral of 1 over y squared is negative 1 over y. The integral of 1 over x squared is negative 1 over x. And of course, as soon as you get done doing your integral symbol, slap a plus c on that thing and solve for it. Now, how in the world am I going to solve this? Well, first things first, there's a negative here. Let's multiply both sides through by the negative. So 1 over y is 1 over x minus a constant. But again, a constant, when you multiply by a negative or a positive or a plus or minus, or you take a root of it, or you do e to it, it's still a constant. So that means 1 over y equals 1 over x plus some constant. Is it the same constant as down here? No, I keep labeling it c because I'm lazy. But Whenever you change your constants, that's okay. Just kind of, when you apply your initial conditions, you'll figure it out. Now, how am I going to solve for y from here? Y is on the bottom of this fraction, so I can flip the left side of my equation if I also flip the right side of my equation. Unfortunately, well, on the left, it's easy. Flipping 1 over y is just y. On the right, flipping this whole thing is over 1, so flipping it will be 1 over this whole thing. Multiplying the top and bottom of this fraction through by x, you get that 1 times x is x. On the bottom, multiplying by x, c times x is cx. X times 1 over x is 1. So y equals x over cx plus 1 is a pretty good solution for y right there. But they gave you an initial condition. When x is 1, y should be 1. So I can use that information and plug things in to figure out the constant should be. And let's see what it is. So let's see, if y is given by this equation, I should get out 1 when I plug in 1. So 1 equals 1 over constant times 1 is constant plus 1. So if you multiply both sides by c plus 1, then c plus 1 must equal 1, and therefore the constant must be 0. Oh, that worked out nice. So that means that, going back to my equation up here, this is the solution I had, y equals x over a constant x plus 1. Since the constant is 0, well, 0 times anything is 0, plus 1 is 1, so I just have x over 1 or x. So the specific solution for this is called y equals x. This right here is called your general solution. It's a general solution because it works for any constant, any initial conditions, and it always solves this initial differential equation. This is called a specific solution because it specifically applies in the specific solution to this initial condition they give you. So general solution, specific solution. If they give you a boundary condition, you plug it in, you will get a specific solution out. There should be no more constants. You say, hey, y equals x. And it works. If you take the derivative of this, let's check it too. First of all, when you plug in 1 to get out 1, well, pretty obviously so. 1 equals 1, duh. Does it satisfy the derivative thing? Well, what's dy over dx? dy over dx is 1, right? So basically this is saying x squared is y squared. And since y equals x, and you square both sides, yeah, y squared equals x squared. So this does, in fact, satisfy this boundary condition and the original. And last example from just the lesson is this one. 1 over y dy over dx is cosine of x. So again, start off by multiplying by dx. And when you do, great. All the x stuff is on the right and all the y stuff is on the left. It's already separated. Awesome. So we'll slap some integrals on this thing. Integral of 1 over x should say, oh, that's a typo. What should that say? I should say natural log of absolute value of y. I'll fix that for you before I upload the PDF. And the integral of cosine of x is sine x. So you have natural log of the absolute value of y equals sine x plus c. And then, well, let's see if we can get to the y that's supposed to be here. It's buried inside of a natural log, so let's do e to both sides. Again, the trick is if you have e to something plus something, you can break it up. So that's e to the constant times e to the sine, but e to the constant is another constant. And then on the left, the e and the natural log cancel out, so you have the absolute value of y is a constant times e to the sine x. Again, if the absolute value of something is a number, then that something inside the absolute value must be plus or minus the number. Well, plus or minus a constant is another constant, so I kind of just drop that. And there we go. There is our general solution for this. It's got y solved for. Y is some constant times e to the sine x, which apparently solve this differential equation. Specific to us, though, we want when we plug in 0 for x to get out e for y. So let's see what happens when we do that. So let's see. If you plug in 0 for x, you should get out e for y. When you plug in 0 on this side, you get sine of 0, which is 0, e to the 0, which is 1, and 1 times the constant is the constant. So on this side, it's just a constant. I should get out e. So the constant is e. And plugging that back in to our general solution right here, that means y is e times e to the sine x. Since these have the same bases, I just might as well put them together. This is e to the first, so I can combine them and call it e to the 1 plus sine x in the exponent. And the specific solution to this boundary equation, to this differential equation, is y equals e to the 1 plus sine x power. And that's it. It's really straightforward. I mean, these are rinky-dink little, the simplest, differential equations you could have. But a lot of things can be solved this easily if you can separate things. So it's a good skill to have. Now, if you get to college, you'll take a whole course on differential equations. They'll tell you a whole bunch of techniques to try to solve things that are more complicated. But at the heart, this is what differential equations is. This is all the whole course is. Trying to find techniques or strategies or ways to figure out what is y based on the setup you have. And that's the entire course on it. But it is complicated, and some of them you just really can't solve. So, you can solve pretty much every, a lot of them, even first order differential equations, you cannot solve explicitly and say, okay, y equals this or something like that. So, but I'll let a future course and future teacher deal with that for you guys. But this is just exposure to it. Okay, so as promised, here as always is something from your homework. This is number 16 from it. And it says, find the general solution. That just means, plus a constant, that doesn't mean there's some, and if you notice, there's no boundary condition given. So how could I possibly find a specific solution if I don't have a specific point to use? Find the general solution, and if possible, write it in, some kind of explicit form, or y equals this. Okay. So here's our equation, y prime, and they might write y prime because they're lazy, is 2 over xy plus y. Now, it's very important to write y prime as dy over dx, so you can see that I'll multiply both sides by dx or whatever. And also down here on the bottom, how in the world are you going to get these x's and y's to kind of be separated? Well, they both have a y in them. So also, algebraically, what I'm thinking about doing on the bottom is just maybe factor a y out of that bottom expression. And this is something that looks a little easier to separate out than this stupid thing was. But again, multiply by dx, so move the dx to this side. And then on this side, you have all x stuff except for this divide by y. This y is kind of in the way. So we want to move that to the other side, multiply both sides by y. So if you do all that, then all the x stuff is on the right, and all the y stuff is on the left. They're on separate sides. Awesome. Now we just got to slap some integrals on it and proceed from there. Integral of y with respect to y is 1/2 y squared, obviously. The integral of 2 over x plus 1 is 2 times the natural log of the absolute value of x plus 1. And of course, since we just got done doing our integral, plus a constant. Now, can we solve for y? Well, we can try. So multiply both sides by 2. Y squared would be 4 times the natural log of x plus 1. And then, of course, a constant times 2 is just another constant. And how do you want to do the square? With a square root. So square root the entire side. Don't forget a plus or minus. And there you go. There's my explicit form of my solution for this. Plus or minus this thing. There are 2 possible answers. The positive function of this, the negative function of this. Just like there's usually 2 branches of a square root function. There's the positive square root that we're usually using, the negative square root that we usually use plus or minus all the time. So I doubt that this is actually a function, probably some kind of relation. But this is as far as I can go, and this is an acceptable answer because you got y by itself, and you got your plus or minus. Note the plus c is under the root. I know you're always used to having a plus c off to the end, and there will always be a plus c off to the end as soon as you get with your integral. But actually solving for the y after that, the c might end up under a root. It might be e to a constant, and then that turns into a constant times something. So every case is different. But again, the key thing is they write y prime, write dy over dx, multiply by dx, get all the x stuff on one side, get all the y stuff on the other side, integrate, got your arbitrary constant, and if they happen to give you some kind of boundary condition, then plug those in so you can figure out the constant actually is. It's really simple, guys. Straightforward lesson today, and I don't think you guys are going to have too much trouble on the homework either, so you're good. All right, you guys got your homework over Taylor series due today. You got your 7.1, that's what this is, over simple separable differential equations. And don't forget, if you want that extra credit for your mastery things on your integrals, just practicing those, feel free to turn those in anytime. They can be turned in early, but it's due on the 6th. And again, 8th will be the very last day of the course officially. But check your course schedule. I think we're even done like a day before that or something like that. So, but 8th is the cutoff. And after that, I'm going to put all the grades in the Yosho, and I'm going to finalize your guys' things, and we're going to be done. And you can focus on any of your other remaining courses for the last week or so of class. All right, guys, that's it. Nice seeing y'all sometimes during the help sessions, and I'll see you on the next one. So work on this one. Keep up the good work. I got a few lessons left, and I will talk to you.